College Algebra, Chapter 3, Section 4, Further Applications of Quadratic Functions and Models. What we're going to be looking at in this section are applications of what we've already talked about. And as you know, with math, applications generally means word problems. So hang on, we're about to do a bunch of word problems involving quadratic equations. The first one looks like this. We have a farmer who wants to enclose a rectangular region. He has 120 feet of fencing and plans to use one side of his barn as part of the enclosure. Let x represent the length of one side of the fencing. We're going to determine a function that represents the area of the region in terms of x. And we're going to look at what are the restrictions on x. And we're going to graph the function in a viewing window that shows both x-intercepts and the vertex of the graph. Then we're going to interpret the point on the graph 18, 1512. We're also going to answer what is the maximum area the farmer can enclose. Now, if you want to be brave and try this one on your own, pause the recording, give it a try, and then resume the recording and see how you did. First, we're going to find the function that represents the area of the region in terms of x. It's a very good idea with these problems to draw a diagram, so you see that on the left. We have the barn wall for one side, the two sides that connect with the barn wall. We've labeled x. There will be x amount of fencing on each of those two sides. The third side, the one that is parallel to the barn wall, will be the remainder of the fence. Since we had 120 feet to start with, the remainder of the fencing will be 120 feet minus the two x's on either side, so 120 minus 2x. As far as the area goes, we know the area of a rectangle is length times width, so we have that a of x, the area, equals x times 120 minus 2x, and when we distribute and put it in standard form, we get negative 2x squared plus 120x. Part B asks for the restrictions on x. Since this is an application problem, there are certain numbers that would not make sense. Since x represents the length of a fence, then it must be greater than 0. Also, 120 minus 2x, which represents a length of fence, must be greater than 0. Solving for x, that gives us x must be less than 60. So we know that x must be somewhere between 0 and 60 feet. Part C tells us to graph the area, and you see that here. We want it in a viewing window that shows both the x-intercepts and the vertex of the graph. So you need to make sure your graph is the appropriate size. Notice that we are going for x from about negative 10 to 94 here. You don't have to go quite that far out. We know that x must be between 0 and 60, so 94 is kind of beyond that. You can bring the x value in some if you wish. And then for the y value, we're going between negative 300 and 2000. You may need to experiment with the window a little bit to make sure you see all the parts of the graph that you need to see. And then we're asked to interpret the point 18, 15, 12. Remember, 18 is our x value, and our x value represents the length of one of the sides of the fence that connects with the barn. So the two sides of fencing there that connect with the barn are each 18 feet. And when that happens, when you have 18 feet on the two sides of the fence that connect to the barn, the area of the barn then will be the fenced in area, will then be 1,512 square feet. In other words, A of 18 equals 1,512. And you can double check that by putting in the information to the equation. And then finally, what's the maximum area that he can enclose? Well, the maximum value, as we have said before, occurs at the vertex. So you have a couple things you can do here. You can use your graph to figure it out, or you can use the fact that the vertex, at least the x value, is where x equals negative b over 2a. So we're going to use 120 for b, and a is negative 2. Putting those into negative b over 2a, we get 30. So the maximum value is going to occur when the two side portions are 30 feet each. And then you can also figure out that remaining side if you want to. But the question was, what is the maximum area? So we'll put in 30 for x and we find out that the maximum area he can enclose will be 1,800 square feet. Now we're going to work with the volume of a box. A machine produces rectangular sheets of metal, satisfying the condition that the length is 3 times the width. Furthermore, equal size squares measuring 5 inches on a side can be cut from the corners so the resulting piece of metal can be shaped into an open box by folding up the flaps. We're going to determine a function v that expresses the volume of the box in terms of the width x of the original sheet of metal. We're also going to find the restrictions that must be placed on x, just like before. If specifications call for the volume of such a box to be 1,435 cubic inches, what should the dimensions of the original piece of metal be? And then finally, we're going to find what dimensions of the original piece of metal will assure a volume greater than 2,000 but less than 3,000 cubic inches. We're going to solve that graphically as well. Now again, if you're brave and you want to give this a go on your own, pause the recording and go for it, and then resume the recording to check your answer. Okay, let's look at A and B first. A says to determine a function v that represents the volume of the box in terms of the width x of the original sheet of metal. So again, we've drawn a couple of sketches here. The machine produces a metal where one length is 3 times the other. So drawing a rectangle, we have x and 3x. Now you'll notice the red dotted lines. Those represent the folding points, and then the red lines and the red right angles there represent the parts that are going to be cut out in order to fold this up and make a box. Okay, so what we need to do then is figure the length and the width of this box. Well, the length of the original sheet of metal is 3x, but then we're going to remove 5 inches from each side. So that's going to be 3x minus 10. The width of the original sheet of metal is x, but again, we're going to remove 5 inches from each side, and that gives us x minus 10. And it just so happens that the box will be 5 inches high, the exact amount that we're cutting out. So our volume is going to be 3x minus 10 times x minus 10 times 5. You do need to FOIL that out, the 3x minus 10 times the x minus 10, and then multiply the result by 5. And we get 15x squared minus 200x plus 500. Now again, we're asked to consider what restrictions must be placed on x. And again, this is a piece of metal. The dimensions must be positive. So that means that 3x minus 10 has to be greater than 0, and our x minus 10 has to be greater than 0, which gives us that x is greater than 10/3 and x is greater than 10. Both conditions are satisfied when x is greater than 10, so we're going to say that x has to be 10 or greater. Part C, if the specifications call for the volume of the box to be 1,435 cubic inches, what should the domain of the original piece of metal be? We'll just take our volume equation that we found in part A, and set that equal to 1,435. And you see we've done that here. We subtracted that from both sides to get it in the proper form, and here we actually factored it. We got 15x plus 55, or x minus 17. That gives us negative 11/3 and 17. Negative 11/3 does not even make sense because remember again, x is the length of a side of a piece of metal and we cannot have a negative length. So that only leaves us with x equals 17. We already said x needed to be bigger than 10. So the original dimensions have to be 17 for this one side that's x, and then the side that's 3x will be 51. So 17 inches by 51 inches. And then finally D, what dimensions of the original piece of metal will assure volume greater than 2,000 but less than 3,000 cubic inches? Solve it graphically. So what we're going to do is we're going to put our equation, our volume equation, into y1, and we're going to put y2 at 2,000 and y3 at 3,000. And our answer is going to be what's in between the two. We find these points of intersection. We find that at 2,000, x is 18.7, and then when y is 3,000, x is 21.2. And again, this is for x greater than 10. So our dimensions for x need to be somewhere between 18.7 and 21.2 inches. And then you can use those to find the matching length values. If x is 18.7, then the other side must be 56.1. And when x is 21.2, then the length must be 63.6. Continuing with our geometric theme here, we're going to work a problem that requires the Pythagorean theorem. Now, in case you've forgotten that, the Pythagorean theorem is a theorem that deals with right triangles. It says that the square of the lengths of the two legs of a right triangle must total the third side, the hypotenuse squared, or a squared plus b squared equals c squared. This says that the longer leg of a right triangular lot is approximately 20 meters longer than twice the length of the shorter leg. The hypotenuse is approximately 10 meters longer than the length of the longer leg. Estimate the lengths of the sides of the triangular lot. Now again, pause this recording if you want to give this a try on your own, and then resume to check your answer. First of all, we're going to let S be the length of the shorter leg in meters. So the shorter leg is S. Then the longer leg is 20 meters longer than 2 times the shorter leg. So 2S plus 20 is the longer leg. And then the hypotenuse is 10 meters longer than that. So 2S plus 20 and then plus 10, or 2S plus 30, is the length of the hypotenuse. So this is what our triangular lot looks like. The shorter leg is S, the longer is 2S plus 20, and the hypotenuse is 2S plus 30. And then we're going to apply the Pythagorean theorem. The shorter length S squared plus the longer leg squared, 2S plus 20 squared, equals the hypotenuse squared, 2S plus 30 squared. You must FOIL out these parentheses. You cannot say 2S plus 20 squared is 4S squared plus 400. Notice we can't do that. It's 2S plus 20 times 2S plus 20. You must use FOIL. So we have the next line, S squared plus 4S squared plus 80S plus 400 equals 4S squared plus 120S plus 900. Then what we're going to do is get everything on one side of the equation. We're going to combine like terms, and we're going to get this quadratic equation in standard form. That gives us S squared minus 40S minus 500 equals 0. This can be factored. Negative 50 times 10 gives us negative 500, and negative 40 plus 10 gives us, negative 50 plus 10 gives us negative 40. So we're going to use S minus 50 and S plus 10. Putting each of these equal to 0 and solving, we get that S is 50, or that S is negative 10. Now again, use some common sense. S is the length of a side of a triangular lot. You do not use negatives to measure that. So we throw out the negative 10 answer because it doesn't make any sense for this problem, and we get that our shorter side is 50, our longer side, our longer leg, is 120 meters, and then our hypotenuse is 130 meters. Okay, this is on the graphing calculator. What we did here was we let y1 equal x squared plus 2x plus 20 squared, which was the left-hand side of the equation, and y2 is 2x plus 30 squared. Now what they did here is they actually graphed y1 minus y2 and looked for the x-intercept. And the reason for that is that the y values are very large. So you can do it that way, or you can, even once we got it into a standard form, you can graph that instead. So graphing it, we find that the x-intercept is 50, which supports the answer that we got analytically. Now we're going to work with a quadratic model. We're going to be given a table of data, and this is the percent of Americans 65 and older for selected years. You'll notice the selected years go up to 2040. You'll also notice that 2020 and 2040 have an asterisk. Those are projected percentages, obviously, since we haven't actually reached those years yet. We're going to plot the data, letting x equals 0 correspond to 1900. So 1900 is 0 for x, 1920 will be 20, 1940 will be 40, 1960 will be 60, 1980 will be 80, 2000 will be x equals 100, 2020 will be 120, and 2040 will be 140. We're then going to use 2 points, 0, 4.1 is the vertex, and 140 to 20.6, or you could choose another point if you want for that one. And we're going to put it into the f of x equals a x minus h squared plus k, and figure out what a is and make a quadratic function that will possibly fit this model. We're going to graph the equation we come up with in part B in the same viewing window as the data that we plotted in part A and see how well it matches. And then we're going to let our graphing calculator do the heavy lifting and let it come up with an equation using the quadratic regression feature on it. So again, if you want to give this a try on your own, pause the recording. If you're wondering where the quadratic regression is, if you remember doing linear regression, it's in that same menu. If you decide to work this on your own, go ahead and pause and then resume the recording to check your answer. So the first thing we need to do is plot the data. And again, remember 1900 is going to be represented by 0. What you want to do to plot the data is you want to push the button that says Stat and then go to Edit, and it will bring you to the lists. And for list 1, you want to make list 1 your X list. So notice we put all the X values there, 0 all the way. You can't see 140, but it's at the bottom. What you need to do is you go down, you put in the 0, you hit enter after every entry. For list 2, you're going to put in your Y values. And it's really important that you pay attention to what you're doing. If you mismatch the size of the list, calculator will not do the graphing for you. It'll tell you made a mistake. Then what we're going to do to actually graph it, what you need to do to graph it is you need to hit, it's the second Y equals button. It should say stat plot. You're going to choose one of the stat plots and hit enter. You're going to make sure it's turned on at the top. You should already have it set for the settings that you want, so everything should be good. You shouldn't really have to change anything else. You want what's called a scatter plot. It just looks like a bunch of dots. I believe it's the very first item on the style menu. And you want to make sure that your X is list 1 and your Y is list 2. Once you have the stat plot turned on, hit second mode to quit. And then what we're going to do is we're going to go to our zoom button, and you're going to choose zoom stat. And this is going to allow the calculator to make a window based on the lists that it knows you're going to use now that you've turned the stat plot on. And once you do that, it should graph it for you, and you should have a graph similar to what you see here on the screen. Okay, for part B, we're going to take f of x equals a x minus h squared plus k, and we're going to use that to develop a model for the data by putting in 0, 4.1 as our vertex, so that'll go in place of h and k. And then we're going to use the point 140, 20.6 as x and y, or x and f of x, to determine a. So you can see here that we substituted, put those numbers in, we solved for a, and we got 0.000841 for a. So our equation is f of x equals 0.000841 x squared plus 4.1. Now for C, we're going to graph that function in the same viewing window. This is pretty simple to do. You've already got the graph of your points in there, so what you're going to do is hit the y equals button and just put this equation in, and it will graph it right in there with your points. And then we're going to ask ourselves, how well does it fit? And it fits okay, but we got some points in there that don't quite match. So we're going to see if we could get a little better fit. What you're going to do is use the quadratic regression feature, and how you find that is, again, you're going to hit the stat button, and this time you're going to go to calc, and you're going to go down until you find quad, QUAD, reg, R-E-G. It stands for quadratic regression. So QUAD, R-E-G. You're going to select that and hit enter, and you should have something similar to what you see here pop up on the screen. First, it tells you y equals ax squared plus bx plus c. That's to tell you the form of the equation. Then we have that A equals 4.985119 E negative 4. What that means is you're going to put a decimal, 3 zeros, and then 4.985119 for A. That's scientific notation there. For B, we've got 0.045267857. And then for C, we have 4.054166667. So what you're going to do is jot that down, and you're going to put that in the y1 instead of the equation we came up with earlier. And when we do that, we can see that we do have a much better fit. Now again, the points in the middle aren't the greatest fit, but they're a lot closer than what we originally had. The rest of this are some examples you can try on your own. So for the rest of the recording, pause the recording, give the problems a try, and resume the recording to check your answer.